Hi guys, okay, this is a video I've wanted to make for quite a while. This is the Fundamental Theorem of Calculus. So, right before I get into it, let me just first state, guys, that you don't need to know this for your exam, for your IB exam at least. However, it's very interesting. And for anyone who is interested in maths and calculus and is interested in how this whole thing works, why the derivative and the integral are connected, why this area function, the area under the curve, is found by getting this integral, which is like the antiderivative of a function, this video will hopefully explain all that. So we're going to start with a function. Now I'm going to call this function, or the graph of this function, y is equal to f of t. So we have some curve like this. Okay, some curve, doesn't really matter what curve we're talking about. And we're going to define, okay, let us define an area function. So we're going to go from some initial value over to some other value. Let's call this a, and we're going to call this x. Now the reason I've chosen t here, sometimes this is called a dummy variable, is because I am going to use x as the variable in the integral, so I don't want to use that x as the variable of the function. So this function is y is equal to f of t, and some value of t is x, if that makes sense. Okay, so we're going to define the area function as the area from some a to some x. So a is like our initial value and x is the thing that's going to move. So this is a of x. This area, if you like, in here, all this area is a of x. Okay, now we're going to call this weird integral thing. We're going to say, okay, a of x is equal to the integral from a to x of f of t dt. So we're starting with this. This is what we're defining this to be. The area from a to some x, we're going to put it as this using this notation. Okay, this is the area function. Now, consider, we're going to move along here a bit, and we're going to go to another value here. So I'm going to go just a little bit beyond x. Okay, now I'm going to put this x over here so we're clear that that goes there. And this is x plus h. Now, if you've studied calculus a bit, you may recognize this kind of way of working. We have our x value, and x plus h is an x value that's a little bit to the right of x. Now, we will be taking limits later, but just for now, assume it's some x value a bit to the right, or h to the right. Okay, now the area of this like strip here, the area under the curve between x and x of h, this is equal to the area x plus h, because this is the area from a to x plus h, minus a of x. Because if we get the area to here and we subtract the area to here, we get the red area. Okay, hope that makes sense. So we can say that this area here is a of x plus h minus a of x. Okay, now I'm going to kind of zoom in on this here a little bit. Imagine I'm zooming in there, and I have here, this is my x, and here, this is my x plus h. So imagine we've just zoomed in there. So this and this red area, if you like, is my a of x plus h minus a of x. This area is actually somewhere between the area of this rectangle here and this rectangle here. So that means that a of x plus h minus a of x, that's our red area, has to be less than or equal to. Now, this rectangle, what is the width of the rectangle? Well, the width of the rectangle from here to here, this is just h, because this is our x and our x plus h. So this width is h. And the height of the big rectangle is f of x, because this kind of, the length of this line here is f of x, because it's just going from here up to here. The y value, if you like, is f of x. And the y value of this one, so the height of this rectangle, is f of x plus h. Now this is the smaller one, and this is the bigger one. So this means the area, the red area, must be less than, h, this, times f of x. That's our width times height, area of a rectangle. And it must be greater or equal to h times f of x plus h, which is this one. So it's somewhere between these two. Now, just to clarify, if this was an increasing function, because it works for increasing or decreasing functions, you would have a similar kind of situation, except the opposite. So imagine this is our x, and this is our x plus h. This is our red area. Well, the big rectangle is now this one, and it's going to be our, this is our, again, h from here to here, and this is our, oh sorry, this is h, so this is our small rectangle, which is actually going to be h times f of x, and our big rectangle is going to be h times f of x plus h. So similarly, I can say, so this is for, let me just say, guys, this is for a decreasing function. Let me move this down slightly here. This is for decreasing. And then for increasing, we're going to have something similar, but it's going to be a of x plus h minus a of x, that's our red area again, is less than or equal to, now the small one is h times f of x, and the big one is h times f of x plus h. So it's less than h times f of x plus h, and greater than the small one, which is h times f of x. Okay, now if I divide everything by h, now h is a positive number because it's just this distance here, I can do this without messing up the inequality. So I'm just going to divide everything by h. I get f of x is less than or equal to a x plus h minus a of x all over h, and I'm dividing this by h too, so this is f of x plus h. So I've basically divided everything by h. Okay, now I'm going to remove these guys just so I have space to work with here. This is the cool bit. So we know this is between here, but if I take the limit, so taking the limit as h approaches 0. So as this h gets super, super small, as h approaches 0, what happens? Well, we're left with, let's just look at this guy down here, we're left with f of x, because there's no h here within f of x, it's f of x, is less than or equal to the limit as h approaches 0 of this thing here, this a x plus h minus a of x over h. And then what does this equal as h approaches 0? Well, this becomes f of x plus 0. F of x plus 0. Now, this is the really cool bit. What is the limit of this as h approaches 0? Well, if you've done, this is the key to the whole thing, guys, as far as I'm concerned. If you have done differentiation from first principles, you will recognize that this is the derivative. This is a dash of x. It is the derivative of this area function. And this means that it is between f of x and f of x plus 0 is just f of x. Now this is why it works for both the increasing and decreasing functions. It doesn't matter which way around it is. You're going to get that this area function is between f of x, or sorry, the derivative of this area function is between f of x and f of x, which actually means, therefore, a dash of x is equal to f of x. So the derivative of the area function is equal to the function itself. Okay, now, so that's the first really cool bit. Then, guys, we say, right, this is the derivative of the function. So what is the area function itself? Well, if the derivative of the area function is f of x, the area function must be the thing that we differentiate to get f of x. And that is where this term, the antiderivative, comes from, which you may have heard before. And you may have seen this notation in textbooks and papers or whatever. But the antiderivative of f of x we often write as capital F of x. So a of x is f of x, capital F of x, where f of x is the antiderivative. And we do a plus c, because if we differentiate both sides here, we differentiate this, we get a dash of x, differentiate this, we get f of x, and then there must be a c, or there can be a c, a non-zero c, that we differentiate, and we get nothing, because the derivative of constant is nothing. So a of x is equal to f of x plus c, capital F of x plus c. Okay, then we can say, but wait, we know the area of a of a, which is going to equal f of a plus c. We know that a of a, which is the area from a to a, if you like. Well, the area from a to a, if we're starting at a, what's the area between a and a? Well, this is actually 0. So this is equal to 0. So 0 is equal to f of a plus c, which means c is equal to negative f of a, which then means the area function, a of x, is equal to f of x plus c, which is now minus f of a. And then we can go back to this funny integral sign thing that we defined at the start and say, okay, that means the integral from a to x of f of t dt is equal to capital F of x minus f of a, where this capital F is the antiderivative. And finally, we can then say that the integral from a to b, to some b here, of f of t dt is equal to f of b minus f of a, which will give us the area between a and b, and these are what we call the limits of integration. So that's it, guys. That is the fundamental theorem of calculus. That is why the derivative and the integral are related. Hope that makes sense, and yeah, keep following for more interesting videos.